Welcome to this presentation on the kinetic molecular theory of gases. This fundamental theory in physical chemistry explains how the behavior of gases at the macroscopic level emerges from the motion of individual molecules. Developed over the 19th century by Clausius, Maxwell, and Boltzmann, the kinetic molecular theory provides the theoretical foundation for the ideal gas law and connects the invisible world of molecular motion to measurable properties like pressure, temperature, and volume. By the end of this presentation, you will understand how 5 simple postulates explain why gases expand to fill containers, why they exert pressure, and how temperature relates to the average kinetic energy of molecules. The kinetic molecular theory is built on 5 fundamental postulates. First, gases consist of a large number of tiny particles in constant, random, straight-line motion. Second, the volume of individual gas particles is negligible compared to the container volume, so particles are treated as point masses. Third, intermolecular forces between gas particles are negligible, except during collisions. Fourth, collisions between gas particles and with container walls are perfectly elastic, meaning no kinetic energy is lost. Fifth, the average kinetic energy of gas particles is directly proportional to the absolute temperature. These postulates define the ideal gas model. Gas particles move in straight lines at constant speed between collisions. Their velocities follow a statistical pattern called the Maxwell-Boltzmann distribution. Not all molecules have the same speed. Some are slow, some are average, and some are very fast. As temperature increases, the distribution broadens and shifts to higher speeds. 3 characteristic speeds are particularly important. The most probable speed Vp is the speed at the peak of the distribution. The average speed V av g is the arithmetic mean, and the root mean square speed Vrms, which is used in kinetic energy calculations. All 3 speeds are proportional to the square root of temperature divided by molar mass. Pressure is a macroscopic manifestation of billions of microscopic collisions between gas particles and container walls. Every time a molecule hits the wall and bounces back elastically, it transfers twice its momentum to the wall. The total force from all these impacts, divided by the wall area, gives us the pressure. The kinetic molecular theory derivation of pressure is elegant. Starting from individual collisions, we sum over all particles and find that pressure equals 1/3 times the number density times the mass times the mean square speed. From this, we derive the ideal gas law. Pressure is proportional to both the number density of molecules and their average kinetic energy. Temperature is a measure of the average kinetic energy of gas particles, not the total kinetic energy. This is one of the most important concepts in physical chemistry. Absolute temperature is directly proportional to the mean translational kinetic energy per molecule. The average kinetic energy per molecule equals 3/2 times Boltzmann's constant times temperature. Boltzmann's constant is 1.381 times 10 to the negative 23rd joules per Kelvin. At the same temperature, all ideal gases have the same average molecular kinetic energy, regardless of their molecular mass. Light hydrogen molecules must move much faster than heavy oxygen molecules to have the same kinetic energy. At room temperature, the average kinetic energy per molecule is about 6.2 times 10 to the negative 21st joules. The ideal gas law, PV equals nRT, emerges directly from the kinetic molecular theory. This single equation combines all 5 postulates into a powerful relationship, connecting pressure, volume, temperature, and the amount of gas. The gas constant R has a value of 8.314 joules per mole Kelvin, or 0.08206 liter atmospheres per mole Kelvin. Starting from the KMT pressure equation and combining it with the temperature-energy relationship, we derive the ideal gas law. PV equals nKT is equivalent to PV equals nRT, since N equals N over Avogadro's number and R equals Na times Kb. The ideal gas law encompasses Boyle's law, Charles's law, Avogadro's law, and Gay-Lussac's law. All the classic gas laws can be derived from the kinetic molecular theory. Boyle's law states that pressure and volume are inversely proportional at constant temperature. When you squeeze a gas into a smaller volume, the molecules collide with the walls more frequently, increasing pressure. Charles's law says that volume is directly proportional to absolute temperature at constant pressure. Hotter molecules move faster and hit the walls harder, so volume must increase. Avogadro's law states that equal volumes of gases at the same temperature and pressure contain equal numbers of molecules. Gay-Lussac's law relates pressure directly to temperature at constant volume. These combine into the combined gas law. Diffusion is the spontaneous mixing of gases due to random molecular motion. Effusion is the escape of gas molecules through a tiny hole into a vacuum. Graham's law states that the rate of effusion or diffusion is inversely proportional to the square root of the molar mass. This means lighter gases move faster. Helium effuses about 2.83 times faster than oxygen. Hydrogen effuses 4 times faster than oxygen. Graham's law is derived directly from KMT because the effusion rate is proportional to the average molecular speed, which is inversely proportional to the square root of molar mass. Real gases deviate from ideal behavior, especially at high pressures and low temperatures. The ideal gas law assumes point particles with no intermolecular forces, but real molecules have finite volumes and do attract each other. Johannes van der Waals modified the ideal gas equation in 1873 to account for these deviations. The parameter A corrects for intermolecular attractions. The parameter B corrects for the finite volume of molecules themselves. At STP, most gases deviate less than 1% from ideal behavior, making the ideal gas law an excellent approximation. This work earned van der Waals the Nobel Prize in 1910. The equipartition theorem states that each quadratic degree of freedom of a molecule receives an average energy of 1/2 kBt. A monatomic gas has 3 translational degrees of freedom, giving total average kinetic energy of 3/2 kBt per molecule. Diatomic molecules like nitrogen have additional degrees of freedom. At room temperature, they have 2 rotational modes active, giving 5 degrees of freedom total. The internal energy of an ideal gas depends only on its temperature and the number of degrees of freedom. This explains the heat capacities of gases. Gas molecules collide with each other billions of times every second. The collision frequency Z describes how many collisions a single molecule experiences per second. The mean free path lambda is the average distance a molecule travels between collisions. For air at standard conditions, each molecule undergoes about 7 billion collisions per second and travels only about 68 nanometers between collisions. At lower pressures, the mean free path increases dramatically. In a vacuum chamber at 10 to the minus 6 atmospheres, the mean free path can exceed several meters. These concepts are crucial for understanding transport phenomena in gases. Quiz question 1. According to the kinetic molecular theory, what is the relationship between the average kinetic energy of gas particles and the absolute temperature? Option A. Ke is proportional to T squared. Option B. Ke is proportional to 1 over T. Option C. Ke is directly proportional to T. Option D. Ke is proportional to the square root of T. Take a moment to think about this. Remember the 5th postulate of the KMT. Quiz question 2. Which postulate of the kinetic molecular theory explains why gas pressure increases when the volume of a container is decreased at constant temperature? Option A. Gas particles have negligible volume compared to the container. Option B. Collisions between particles are perfectly elastic. Option C. Gas particles are in constant random motion and collide with container walls more frequently at smaller volume. Option D. There are no intermolecular forces between gas particles. Think about what changes when you make the container smaller. Quiz question 3. Two gases, helium with molar mass 4 grams per mole and nitrogen with molar mass 28 grams per mole, are at the same temperature. How do their root mean square speeds compare? Option A. Both gases have the same RMS speed. Option B. Helium's RMS speed is about 2.65 times greater than nitrogen's. Option C. Nitrogen's RMS speed is about 2.65 times greater than helium's. Option D. Helium's RMS speed is about 7 times greater than nitrogen's. Remember the formula? VRMS equals the square root of 3RT over M. Quiz question 4. What is the mean free path of a gas molecule? Option A. The average distance between two gas molecules in the container. Option B. The average distance a molecule travels between successive collisions. Option C. The average speed of a molecule divided by the container volume. Option D. The distance a molecule travels in 1 second. Think about the word free in mean free path. Free from what? Quiz question 5. Which of the following is not one of the 5 postulates of the kinetic molecular theory for ideal gases? Option A. Gas particles are in constant, random, straight-line motion. Option B. The volume of individual gas particles is negligible compared to the container volume. Option C. Gas particles are attracted to each other by strong intermolecular forces. Option D. Collisions between gas particles are perfectly elastic. Remember that ideal gas particles do not interact except through elastic collisions. Problem 1. RMS speed and kinetic energy of gas molecules. Calculate the root mean square speed and the average kinetic energy of nitrogen molecules at 25 degrees Celsius. The molar mass of N2 is 28 grams per mole. Part C. If the temperature is doubled, by what factor does the RMS speed increase? Step 1. Convert 25 degrees Celsius to Kelvin. T equals 25 plus 273.15, which is 298.15 Kelvin. Convert the molar mass to 0.0280 kilograms per mole. Step 2. Calculate the RMS speed using VRMS equals the square root of 3RT over M. This equals about 515 meters per second. Step 3. Verify the units. R in joules per mole, Kelvin is kilogram meters squared per second squared per mole Kelvin. After canceling, we get meters per second. Step 4. Calculate the average kinetic energy per molecule using Ke equals 3 halves kBt. This gives 6.21 times 10 to the negative 21st joules per molecule. Step 5. Alternatively, The kinetic energy per mole is 3,718 joules per mole. Dividing by Avogadro's number gives the same result. Step 6. When temperature doubles, the RMS speed increases by a factor of square root of 2, approximately 1.414. Problem 2. Graham's law of effusion. A sample of hydrogen gas with molar mass 2.02 grams per mole effuses through a pinhole in 4.50 minutes. How long will it take for the same amount of oxygen gas with molar mass 32.0 grams per mole to effuse through the same pinhole? Step 1. Write Graham's law. The ratio of rates equals the square root of MO2 over MH2, which is the square root of 32 over 2.02. Step 2. Calculate the ratio. 32 divided by 2.02 equals 15.84. The square root is 3.98. Hydrogen effuses 3.98 times faster than oxygen. Step 3. Since rate equals amount over time, the ratio of rates is the inverse of the ratio of times. So TO2 over TH2 equals 3.98. Step 4. Solve for the time for oxygen. TO2 equals 4.50 minutes times 3.98, which equals 17.9 minutes. Step 5. Check using Graham's law directly. We get the same result, 17.9 minutes. The answer is 17.9 minutes. Oxygen takes about 4 times longer to effuse than hydrogen. Problem 3. Van der Waals equation application. Calculate the pressure exerted by 2.00 moles of carbon dioxide in a 5.00 container at 300 Kelvin. Use the ideal gas law, then the Van der Waals equation. For CO2, A equals 3.59 and B equals 0.0427. Step 1. Ideal gas law. P equals nRT over V. 2 moles times 0.08206 times 300 divided by 5. This gives 9.85 atmospheres. Step 2. Van der Waals correction. Correct the volume term. V minus NB equals 5 minus 2 times 0.0427 equals 4.9146 liters. Step 3. Calculate the pressure correction term. ON squared over V squared equals 0.574 atmospheres. Step 4. Apply the Van der Waals equation. P plus 0.574 equals nRT over V minus NB, which is 10.02 atmospheres. So P equals 10.02 minus 0.574, giving 7.50 atmospheres. Step 5. Compare. The ideal gas law gives 9.85 atmospheres. The Van der Waals equation gives 7.50 atmospheres. That is a 24% difference. The ideal gas law overestimates pressure because it neglects intermolecular attractive forces. Carbon dioxide molecules attract each other, reducing the measured pressure. Problem 4. Degrees of freedom and heat capacity. For a diatomic ideal gas like nitrogen at room temperature, determine the active degrees of freedom. Calculate the molar internal energy, calculate CV and CP, and determine the heat capacity ratio gamma. Step 1. Identify the active degrees of freedom. A diatomic molecule has 3 translational and 2 rotational degrees of freedom at room temperature. The vibrational mode is frozen, so F equals 5. Step 2. Calculate the molar internal energy. U equals F over 2 nRT. At 300 Kelvin, U equals 6,236 joules per mole. Step 3. Molar heat capacity at constant volume. CV equals F over 2R, which is 20.79 joules per mole Kelvin. Step 4. Molar heat capacity at constant pressure. CP equals CV plus R, which is 29.10 joules per mole Kelvin. Step 5. The heat capacity ratio gamma equals Cp over Cv, which is 1.40. This equals 7/5. Answer: F equals 5, U equals 5/2 RT, Cv equals 5/2 R, Cp equals 7/2 R, and gamma equals 7/5 or 1.40. Problem 5. Mean free path and collision frequency. Oxygen gas at 300 Kelvin and 1 atmosphere. The molecular diameter of O2 is 3.61 times 10 to the negative 10 meters. Calculate the number density, the mean free path, the collision frequency, and the average time between collisions. Step 1. Calculate number density. N over V equals P over kBt. This gives 2.46 times 10 to the 25 molecules per cubic meter. Step 2. Calculate the mean free path. Lambda equals 1 over root 2 pi d squared N over V. This gives 6.4 times 10 to the negative 8 meters, or 64 nanometers. Step 3. Calculate the average speed. V bar equals the square root of 8 RT over pi m. The average speed is 445 meters per second. Step 4. Calculate the collision frequency. Z equals V bar over lambda, which is 6.95 times 10 to the 9 collisions per second, about 7 billion collisions per second. Step 5. The average time between collisions is tau equals 1 over z, which is 1.44 times 10 to the negative 10 seconds, 0.144 nanoseconds. Each atmospheric oxygen molecule experiences about 7 billion collisions per second, traveling only 64 nanometers between collisions. Let us summarize the key concepts of the kinetic molecular theory. The theory rests on 5 postulates: constant random motion, negligible particle volume, no intermolecular forces, elastic collisions, and kinetic energy proportional to temperature. Pressure equals 1/3 N over V times m times mean square speed. It arises from momentum transfer during molecular collisions with container walls. Average kinetic energy equals 3/2 kBt per molecule. Temperature directly measures average translational kinetic energy. The Maxwell-Boltzmann distribution describes molecular speed spread. 3 key speeds are Vp, Vavg, and Vrms. The ideal gas law PV equals nRT emerges from kMt. Graham's law relates effusion rates to inverse square root of molar mass. The van der Waals equation corrects for intermolecular attractions and molecular volume. The equipartition theorem gives each degree of freedom 1/2 kBt, determining heat capacities. Collision frequency and mean free path describe transport properties of gases. The kinetic molecular theory stands as one of the most elegant and powerful frameworks in physical chemistry. By reducing the complex behavior of gases to 5 simple postulates, it successfully explains pressure, temperature, diffusion, effusion, heat capacities, and transport phenomena. The theory derives the ideal gas law from first principles, providing a molecular foundation for thermodynamics. The van der Waals equation extends the model for real gases. KMT introduces fundamental concepts like the Maxwell-Boltzmann distribution, mean free path, collision frequency, and equipartition of energy. These extend into statistical mechanics and materials science. Understanding the kinetic molecular theory bridges the microscopic world of atoms with the macroscopic world we observe every day. Thank you for watching this presentation.